Hello to everyone, here we go in another video. Today we're talking about the exercise related to an unsymmetrical bending with moment m that is applied with a certain angle with respect to the vertical plane individuated from the direction of y. So this plane pi m, the plane where is applied moment m, the total moment m applied, has an inclination of the with respect to the vertical plane that is in this figure is this plane drawn in the with the green pen, has an inclination that is equal to gamma, and gamma is equal to 13 degrees. But the vertical plane is clearly as an inclination with respect to the x-axis of pi over 2 is 19 degrees. So the total angle theta that we studied in the previous lectures as theta is equal to, here theta is equal to pi over 2 plus gamma. So we have 19 degrees plus 13 degrees, so the total angle is 120 degrees. But we can use also the associated arcs for to obtain the equation of the projected moment. So in this case, this moment, the projections are mx with light in light blue arrow and my in yellow pen. So we can note also the direction of mx and of my. You can now understand if these two moments, if these two components are negative components or positive components. In this case, mx, if I look this moment from the point of view of x, so in this direction, I can clearly see this moment that is clockwise. But if I see the moment in direction of y, I see that that this moment is counterclockwise. So in this case, in the first case, from point of x, from point of view of x, I see a moment mx that is clockwise. So for the convention that we studied in the previous lectures, we understood that this moment is clearly positive. So we have mx, I can write just here, mx is clearly measured than 0, because seen from the point of view of x, this moment mx is clockwise. So this moment for our scene convention is positive. But if I look the my from point of view of y, this moment appears to be counterclockwise. So for our convention, my so is negative. The other convention that we have studied also in the previous lectures is such that the moment y tends to bend the left side of the beam. If you see this 3D plot, clearly you now are seeing only the axis y, z, and x. But if you imagine that here there's also the shape of the beam, this is the left side of the beam and this is the right side of the beam if I look the beam from this point of view. Okay, so my for its direction tends to bend the left fibers of the beam. Instead, mx tends to bend the upper fiber of the beams. Mx is the for an association is like the pitching moment of an aircraft, up and down, nose up and down. Here we have flange up and down. So in this case, mx is flange down. In this case, means positive mx. My is like the yaw moment of an airplane. If the nose is oriented from this point of view through the right direction, we have an my negative. I try to explain this convention in many manners. So you use one convention and go on with that convention. So also here we have a trace of the action of the moment m, and we have the vectors mx in light blue and my in with the yellow pen as said before. So now we have understood that this moment m is as an inclination, the plane where is applied this moment as an inclination of about 13 degrees, but that with respect to this axis as an inclination of about theta, that is pi over 2 plus gamma, so is 120 degrees. So this is all the geometrical data. A is equal to 300 millimeters, B 200 millimeters, the thickness is 20 millimeters, the web thickness is 25 millimeters, and the moment applied is 100 kilonewton times meter. So mx and my components, we studied science here. We know that mx is equal to, if I look this right triangle, this is also this angle here that I highlighted in green, in orange. So I switch pen because orange is a quite confusional pen. So this angle is also alpha. So mx is equal to m times cosine of 13 degrees, because clearly here I have just done this step where mx is equal to m times sine of theta, but theta is equal to alpha, gamma in this case, gamma plus pi over 2, but the sine of this quantity, gamma plus 19 degrees, is equal to m times cosine of gamma, but gamma is equal to 30 degrees. So we have finally m times cosine of 30 degrees, where while for my is the opposite consideration, where m is equal to cosine of theta, and it's equal to m times cosine of gamma plus pi over 2, that is equal also minus m times sine of gamma, that is minus m cosine of 30 degrees. But if you take a look to this right triangle here, lighted here, my is clearly equals to m times sine of not alpha but gamma, here is gamma, sorry for that, is negative because for the convention that we stay using in this exercise, and for all others exercise in the future. And so we have these numbers of mx and my, so from Newton times meter to Newtons times millimeter. So now we can move on to the sigma z formula. We have a sigma zeta for x and sigma zeta for y direction. Sigma zx stay x for mx and the moment of inertia axx, but we can switch also this. So if sigma zy and sigma zx, if you mean x and y, the direction y and x where you want to know the bending stress, but use any consideration in this case is similar. So sigma z is equal to the sum of sigma zx and sigma zy, And we have this formula here. This is the main formula to use here. Because we have this formula, we have studied also from the previous lecture that sigma z, the general relation of sigma z is equal to, this is the general formula to calculate the bending stress. And we have this formula. Why? In this condition, because in this exercise we don't apply this formula but this. So this also is a derived formula of this formulation, general formula. Because we have, if you are now practical in this exercise, we have just note that this E-beam shape, or this E-beam, has two symmetrical axes. The first symmetrical axis is the y-axis, and the second symmetrical axis is the x-axis. So the E-beam has two symmetrical axes and is 2 times symmetrical. But if I have a structure or cross-section that has at least one symmetrical axis, I can clearly say that the product of inertia Iyg is equal to 0. If the structure or the cross-section at least has one symmetrical axis, this assumption is verified. So Iyg is equal to 0. So if this structure has 2 times symmetrical, so I can delete this quantity from here, so also this, and I clearly obtain the following formula. So I can simplify xx, Ixx and Iyy here, and we obtain this formulation enclosing the square bracket here. So this is the explanation, because we don't need the total formula of sigma z studied in the theory lectures. But so don't need for completely formula clearly, but we need this formula to obtain the derived formula that is this enclosing in the square bracket. So now we can calculate the moment of inertia. So here I don't report the calculation of the area of single rectangular shapes and of the centroid of singular rectangular shapes, so G1, G2, G3. We have just calculated this quantity in the video, in the previous video, where we seen this beam for the symmetrical bending. So you can go to see this video, and you can see how to derive the G1, G2 and G3 centroid and the area of these 3 rectangular shape. That is the division that we made of the whole E-beam. So, but it's not complicated for this section to calculate all this stuff is. So the 1x and the 2x is the distance from the centroid G1 to the centroid of whole E-beam, and T2 and D2x is the distance from G3 from the whole centroid of the beam. So Ixx1, Ixx2 and Ixx3 are calculated. Ixx3 is clearly equals to the Ixx1 for the symmetry of this beam. Ixx1 is calculated with the theorem of the parallel axis, also known as the Huygens-Steiner theorem. That we have the this is the moment of inertia Axg, so the moment of inertia of the first rectangular shape with respect its own centroidal axis. The area of this rectangular shape multiplied the d1x at square. So if you make this calculus, you can reach this this value 7.85 and blah 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 times 10 at 4 power millimeter at the same power. Ixx2 is equal clearly at this stuff. You can calculate this simply formulation, that is Wt now is our base of the second rectangular shape, and the height of this rectangular shape is a minus 2 times t. 2 times t, clearly all this quantity at third power divided by 12. We have this value of moment of inertia Ixx2. Ixx3 I just explained because is equal to Ixx1. So the total moment of inertia with respect to the x-axis, this axis, is equal to 2 times Ixx1 plus Ixx2, and this is equal to this quantity here. So now we can calculate the moment of inertia with respect to the y-axis. So this is the new thing that we added with respect to the first exercise. The first exercise clearly is for the symmetrical bending. This exercise is for unsymmetrical bending. We just added the inclination of the plane where applied the moment, but now we can add also another consideration, the moment of inertia with respect to the y-axis. So we have simply this formulation now is the flipped formula, if you want, of the Ixx axis, but without the transport moment, because the distance of the clearly here we should have this stuff A1, for instance, times Iyg1 minus Cg. Cg is the center of gravity of or centroid of the wool aircraft, but this quantity Iyg1 minus Ycg is equal to 0, because all this centroid lies on the axis y, so the distance of Iyg1 and from the to Ycg is equal to 0 for both three rectangular shapes. So we have only the moment of inertia with respect to the own centroidal axis, that in this case is the y-axis. So we have Iyy for 1 for first rectangular shape, that is this thing. T is the thickness of the upper flange times b, the length of the upper flange at third power, divided by 12. At the same manner we can calculate as made for Ixx2, we can made the same things, but with a switch on the between the 8 and base of the second rectangular shape, and we have this moment of inertia Iyy2. Also here the Iyy3 is equal for the symmetry to Iyy1, and so the total Iyy is equal 2 times Iyy1 plus Iyy2. So and we obtain this value here, this approximated value here. Now we can move on to the calculation of the equation of the sigma z as a function of two coordinates, x and y. So we have seen before that sigma zeta xy is equal to mx plus times y divided the moment of inertia with respect to x, plus the moment y, the projection of the moment m on the y-axis, times x divided by the moment of inertia that we have calculated just a few seconds ago. And we have this equation here. Now we can apply this equation to do every point that we want to know the sigma z. For instance, we have here the determination of the bending stress along the web. that for the Italian user web I reminded you that is anima, l'anima della, no l'anima dell'immortale, ma è l'anima della nostra trave, sarebbe questa quantità qui, questa qui diciamo colorata in verde. So after a little bit of translation for Italian users, so we have here a sigma z with x equal to 0 and two y coordinate, y1 and y2. That clearly this y1 is this quantity here, and y2 I see the sign, okay, just this quantity, y1 and y2. So upper and lower flange. These two formulation of sigma zeta is also related to the only contribution due to the mx. If you look this equation, because if x is equal to 0, I lost this quantity. This quantity is related to the contribution of my, this quantity here. So I obtain only the contribution of mx. Along the web, clearly, the only moment that produce a bending stress is the mx moment. So if you apply this formula, we obtain this value, 67.5 Newton per millimeter square. So now we can calculate the bending distribution along the upper flange. This coordinate minus 100 and 150 are this point here, AU, CU, BU. AU is a point that has a coordinate of with respect to y is 150. With respect to x is this quantity here, that is clearly negative, and is the half part of the b. So half part of b is 100, so is in the left side of x, so negative x, so is minus 100. If apply this the Boole formulation here and substitute the value of y and x, we obtain this value of the sigma z. So the same thing we can apply for the CU point. The CU point is this point here that has clearly only the y coordinate and x is equal to 0. And we just note that this value is equal to the value calculated here for the sigma z at 150, this value here. So the other point is BU, that this point here, and this point has the same coordinate of IU with respect to y, but opposite coordinate with respect to x. And we have this value here. Now we can calculate the sigma z for the lower flange, but is simple to note that all the coordinates are all the opposite of that used before. So we have the same value but with opposite sign. So this, for instance, these two value is the same as the same point but with the opposite sign. And we have the opposite value of this sigma z. So sigma CL is opposite of sigma CU, and sigma ZBL is opposite to the sigma ZAU. Okay, so now we can see finally the sigma Z distribution taken from the Magsonly book. So we have this distribution of the bending stress along the upper and lower flange. So this is upper flange, lower flange, and this is the distribution along the web. So we note that this quantity here in sigma ZAU, sigma ZCU, the quantity is positive. So this all positive sigma Z. Here is negative, opposite, as said before, this is negative, and this is positive. So Z sigma ZBL is minus 252 and blah blah blah, and we have here, so just here, and opposite of this quantity here on the lower flange is this quantity here that is now positive. But we can calculate also the inclination of the neutral axis, because in this case the neutral axis not is the x-axis, not is this axis here, but is this axis here. This axis that has an inclination with respect to the x-axis of an angle equal to gamma, equal to alpha. So how we can calculate this angle? We know that along the neutral axis, the sigma z is equal to 0. So the point y and a and x and a is any point, a certain point of this neutral axis. So we know also that the ratio between y and x coordinate give us the tangent of alpha. So now we can make the same calculus, and then we have y and a divided by x and a is equal to minus my divided by mx times the ratio of the moment of inertia with respect xx and yy. This is equal to tangent alpha for the analogy. So this is clearly the same thing. So now we want to know the alpha. So in the inverse function of the tangent is the arctan of an angle. So the arctan of this quantity here, is clearly the angle alpha. So alpha is equal to about 76.3 degree. So this is the angle, the inclination angle of the neutral axis with respect to the x-axis, and clearly all the pictures tell us how are the distribution of the bending stress related due to a moment applied on a plane that has an inclination with respect to the vertical direction, that is this direction here, y, of about 30 degrees, as said at start of this video. So this video can finish here, and we will see in the next video. Bye!